Okay, so we're going to now revisit this example that we considered before of a massive pulley with moment of inertia ICM and radius r that has a rope over the top of the pulley connected to two blocks of masses big M and little m. And of course the idea here is if you release these masses from rest, then if big M is bigger than little m, then big M will accelerate downwards and little m will accelerate upwards, and the wheel, the pulley, will undergo angular acceleration and be spinning faster and faster. Okay, so technically this is called the Atwood machine. Okay, and so we're going to revisit this Atwood machine, which we considered before, the dynamics of it. We're now going to consider it, look at it from the point of view of energy. So conservation of energy, delta E total is equal to 0. The total energy in an isolated system never changes. We'll also look at it from the point of view of energy transfer. How is various forms of energy, gravitational energy coming in, going out, energy, kinetic energy going in here, in here, in here, the transfer of energy, work. And we're also going to look at it from the point of view of power, rate at which energy is flowing in various places in this whole system here. So it's a really, really interesting and important example to look at. So the basic idea here, the kind of question we're looking at is, when we release this system from rest, then the system will accelerate. Everything in the system will accelerate, and that acceleration will be constant. So big M will experience a constant acceleration downwards, moving faster and faster downwards. Little m will experience exactly the same magnitude of acceleration, constant acceleration upwards, faster and faster and faster. And at the same time, this wheel, this pulley, is going to be undergoing angular acceleration alpha that's constant. So picking up speed, rotational speed, angular velocity at a constant rate. Okay, so that's happening. And then, so as m is falling, it's picking up speed, and just before it hits the ground, it will have some velocity v downwards, and at exactly the same time, the block of mass little m will have raised up, and it will have a same velocity, same speed, but upwards. And let's suppose that the distance, the height through which m falls, is h. Let's call that h. And the question we're asking is, so as big M and little m undergo constant acceleration, their velocity increases linearly with time to some final velocity v. And at the same time, the pulley is going to be undergoing constant angular acceleration, picking up speed linearly until it finally ends up with some final angular velocity omega. And the question is, what is v and what is omega just before big M hits the ground? Okay, so what else? So let's just say the machine starts from rest. That's one assumption. So all of the velocities, the linear velocities and the angular velocity, are initially 0, and we'll assume that big M is less than little m, so that when we release it, it's big M that accelerates down, and little m accelerates up instead of the other way around. So A and alpha are positive. And what we want to do is we want to find the final values for the linear speeds of big M and little m, and the angular speed, radians per second, of the pulley. Okay, just before big M hits the ground. Okay, so a couple of points just to remind you is, in this situation, this pulley is massive. And so in order to cause an angular acceleration, you need a net torque. And so the net torque comes from the fact that the tension in this rope, we called capital T, is greater than the tension in this rope. So the torque, the counterclockwise torque that the rope under tension T exerts on the pulley, which is the magnitude of the force applied at that point on the wheel, on the pulley, times the moment arm distance, r times t, is a counterclockwise torque, that will be larger than the clockwise torque exerted by the force little t, tension of string little t, rope little t, exerted a lever arm distance or moment arm distance r away. This is a clockwise torque. And the counterclockwise torque is larger than the clockwise torque. So we require that T, big T, is bigger than little t for net counterclockwise torque, okay, which is what causes the angular acceleration alpha. Okay. And the other thing I want to remind you about is that whenever we have objects like this that are in rotational motion, that are connected by ropes to objects in linear motion, there's always a relationship between the linear velocities of the objects in linear motion and the angular velocities of the object in rotational motion. And similarly, there's a connection between the linear accelerations and the angular accelerations. Okay, and so let me just remind you of that. Okay, so if we have a wheel here, pulley, which has some angular velocity omega and is undergoing some change in the angular velocity, rate of change of angular velocity alpha, then, and the radius of the wheel is r, then for a given angular velocity omega, there is a tangential velocity. So the velocity in meters per second at this instant of time of that point on the wheel, that tangential velocity, is equal to the angular velocity omega times r. So this is radians per second times meters is meters per second, is the meters per second velocity of that point on the rim of the wheel. And that is connected to, that point is connected to that point, and they're both moving with exactly the same velocity. So that's that velocity v. So the angular velocity of the thing that's rotating here is equal to v divided by the linear velocity v divided by r. And similarly, the tangential acceleration, the meters per second squared of that point upwards, is equal to the radius of the wheel times the angular acceleration alpha. So this is meters per second squared. Radians per second squared times meters is meters per second squared, tangential acceleration. And this point here is connected to that point. So whatever tangential acceleration this point experiences upwards will be the same as the linear acceleration that little m experiences upwards. Okay, so that's that. Okay, so that's really important. Those are two important things. Okay, and so now we've already analyzed this machine from the point of view of dynamics. So we already know what the acceleration is, so I'll just remind you. So we're going to look at this from the point of view of dynamics, and then energy storage, and then energy transfer, and then power. So the first is dynamics. So from the point of view of dynamics, what we did is we recognized that, yes, we have three objects in motion, big M, little m, and ICM. These are two linear motions. This is an angular motion. You draw a free body diagram for all three of those. You indicate the forces that are acting on this. You indicate the torques that are acting on this. And the net force acting on these objects in linear motion is their mass times their linear acceleration. And the net torque acting on this rotating object will be the moment of inertia, ICM, times the angular acceleration. And then you just solve those three equations, taking into account these relationships, and we figured out what the angular acceleration, the constant angular acceleration, is in this situation of that wheel, of that pulley. Okay, so recall that our answer for the angular acceleration was equal to r times big M minus little m times g divided by ICM plus the sum of the masses times r squared. Okay? And a key point here is that this is constant. And the linear acceleration, a, will just be r times that constant alpha. So it'll be an r squared there. And then you would have the linear acceleration of these masses. And that's constant. So the masses pick up linear speed at a constant rate, and the pulley picks up angular velocity or angular speed at a constant rate. Okay? And so because the angular acceleration is constant, we can use those kinematical formulas we have for angular motion. So we can use this relationship, omega final squared minus omega initial squared is 2 alpha times delta theta. So this is exactly analogous to, v final squared minus v initial squared is 2 times ax times delta x for linear motion. Okay, and we can use this kinematical formula because this alpha is constant. When the angular acceleration is not constant, we don't have a formula like that. We need to use calculus. Okay, So then we say, well, what is this? Well, I don't know. So it's 2 times alpha times what's delta theta. So this is an important thing to understand here. Let me put it down here. Oh, maybe I can put it over here. So I'll make it small over here. So the idea is we have a pulley, and when big M falls through a height h, then the pulley will rotate through, will have some angular displacement. It'll rotate through some angle delta theta. Okay, and so you can figure out that angle delta theta by just looking at this and saying, oh, look, well, this point, this M moves down a distance h, which means a point on the wheel must have moved from here down to here, and that distance, that arc length, is h. Okay, so just transfer that distance h that M falls through, transfer it onto the arc of this circle. And so this distance is h. And you know the radius r, so that you can figure out the angular displacement, the delta theta, for the pulley. Okay, so our situation then looks like this. So this distance here, from here to here, that arc length has to be h. And the radius of the wheel is r. And so the question is, what is the angular displacement, delta theta? Well, we know that h is equal to r times delta theta. So delta theta is h divided by r. Okay, so it's important to learn how to translate linear displacements to angular displacements of the objects, of the rotating object that the linear objects are connected to. Okay, so we have that. And what else? So in this formula here, while omega initial is 0, we start from rest. Okay, and what we're looking for is omega final, which we just called omega. Okay, and so what this tells us is that omega final squared is just equal to 2 times h over r, so 2h over r times this alpha. Okay, and so we're going to multiply by 2h and divide by r. Dividing by r kills that r. We multiply the numerator by 2h. So it becomes 2 times m minus m gh divided by the same denominator, ICM, plus the sum of the masses times r squared. Okay, so that's what omega squared is. That's the final velocity. Now, of course, we're assuming here that m is bigger than m. So this is, really the absolute value here. Okay, because we could make little m bigger than, smaller than, big M smaller than little m, and it would just accelerate the other way. Okay, so we have that, and then, so once we know omega squared, we can then determine omega by taking the square root. Okay, and then, so now we've determined what omega is, the final omega, the final angular velocity of that pulley just before big M hits the ground. So then we can now figure out what that final velocity of big M is, because we know that the velocity of big M in linear motion is just equal to r times the angular velocity of the wheel. Okay, so we figured out what omega is, and so then we can get v is just omega times r. Okay, and so then we're done. So that's certainly one way to solve the problem. Now that involves a fair bit of work. Okay, so you have to draw free body diagrams for all three objects. You have to look at all the forces, all the torques, and apply Newton's second law for translational motion as well as for rotational motion. Solve those 4 equations in 4 unknowns for alpha, and then, given alpha, then you apply some kinematics here, and you get this answer for the final speed. Okay, so you can do it that way. That's certainly one way to do it. However, if we apply the idea of conservation of energy, it's super easy to get this answer here, okay? And so we can think about conservation of energy from 2 different points of view, remember? So we can take our whole system and we can say if there's no energy going in and no energy coming out, then the total energy in that system doesn't change. And so we can write it in the form, 0 is equal to change in the total energy. Okay? Or we can divide the system up and say, well, there's a gravitational energy stored in this part of the system, and there's kinetic energy stored in that part of the system, and so on. And we can look at energy transfers, which is work, which is what we'll talk about next. Okay, but right now we just say, well, we have this isolated system, which is this whole thing, including the gravitational field and so on. And the idea is that the total energy doesn't change. Now, in this case, the total energy, well, there's energy stored in masses in motion, both masses in linear motion and masses in rotational motion. So those are changing, clearly. In fact, they're increasing. Everything starts at rest, and so there's zero kinetic energy in the system. Just before big M hits the ground, both of the masses in linear motion and the mass in rotational motion have kinetic energy. So that's going to be positive, plus a change in the gravitational field energy, and that's got to be negative, so the sum of those two numbers is equal to 0. Okay? So then let's work this out. So 0 is equal to, so the change in the kinetic energy, so there will be a change in the kinetic energy associated with the translational motions of the two blocks, and a change in the kinetic energy associated with the rotation of that pulley. Okay, so there are two contributions to that change in the kinetic energy. So in terms of block big M, we have block big M, the change in its kinetic energy is 1/2 m times its final speed squared minus 0, starts at rest, plus the change in the kinetic energy of little m is 1/2 little m times its final upward speed squared minus the initial, which is 0, okay, plus the change in the kinetic energy of this pulley, which is storing kinetic energy in the rotation of that mass. Instead of 1/2 mv squared, it's 1/2 ICM omega squared. Okay, so it's 1/2 ICM times the final angular velocity squared, which we just called omega squared, minus 0. Okay, so that's the change in the kinetic energy in the system, okay, the total system. And so we need to add to that the change in the gravitational field energy, and that should all add up to 0. And the change in the gravitational field energy is always positive mg delta height. So it's positive big mg times the change in the height. The height final is 0, the height initial is h. So it's 0 minus h, okay? And then plus little mg times height final is h, height initial is 0, so it's h minus 0. Okay, so this this term is negative because big M is falling through height h, so the gravitational field energy is going down. It's causing a negative change in the gravitational field energy. Little m is going up. It's causing a positive change in the gravitational field energy, but not as much. So there's a net negative change in the gravitational field energy. This term is bigger than this term, okay? More negative than, yeah, bigger than that term. So the sum is negative. Okay, great. And so then what we do here is we're trying to solve for the final angular velocity omega. Okay, and so what we do is this equation involves an omega squared, great, but it involves v's over here, linear velocities. But we know that linear velocity v is omega times r. So in these two v's here, we use the idea that v is equal to r times omega. Okay, and then these two terms will be proportional to omega squared, and that's proportional to omega squared. And so we have omega squared terms over here, and then plus terms that are proportional to g, and then, well, let me actually write it out. So what's common to all three of these terms is a factor of a half. There's a half, there's a half, there's a half. And what's also common is an omega squared. So we'll pull that out as well. Let's put that over here. How much room do I need? Okay, so we've pulled out the omega squareds. And so what we have here is an ICM. Okay, that takes care of that one. And then here we have a 1/2 m r squared omega squared. So we have an mr squared from this term and a little m r squared from that term. Okay, so it's a plus big M plus little m times r squared. So that's all of the change in the kinetic energy terms. And then we add to that the change in the gravitational field energy, there's going to be a negative sign. It'll be negative. What's common is G times H. There'll be a negative big M, and then a positive little m times GH. Okay? And so we get that. And then we can just solve for omega squared. And so we get omega squared. This whole thing is equal to 0. So just solving for omega squared, it'll be big M minus little m GH divided by 1/2 of this. So taking the 2 into the numerator, we'll get 2 times m minus m GH divided by this same denominator, ICM plus the sum of the masses, r squared, equals the same as above. Okay, check. Okay, so this actually involved a fair bit of work, but this involves almost no work. It's very easy. Okay, the crucial thing here is when we're talking about changes in kinetic energy, we are now considering not just changes in kinetic energy of masses in translational motion, but also changes in kinetic energy of masses in rotational motion. Okay, great. So this is conservation of energy from the point of view of storage. If energy goes down somewhere, then it has to go up somewhere else, okay, without really any thought for how it is the energy is transferred. Now we're going to look at conservation of energy from the point of view of energy transfer. In other words, the work kinetic energy theorem. So let me just, let's see, I'm going to leave this up and I'll erase this side over here, all right? Okay, so now we're going to look at this same situation, this same Atwood machine. We're going to look at it from the point of view of work or energy transfer. So that's C. So this is work or energy transfer. Now, in general, when you look at something from the point of view of storage of energy, delta E total equals 0, usually that's really easy. And when you look at it from the point of view of work, energy transfer, that's often a little bit more work, no pun intended. But it often, that extra effort is worth it because it gives you additional insights into what's actually happening that are often very interesting. Okay, so we're looking at the Atwood machine from the point of view of work, energy transfer. So the work kinetic energy theorem says that the work done by all of the forces, and now this includes not only forces acting through linear displacements, but also angular forces or torques acting through angular displacements. So that total work done is equal to the change in the kinetic energy of the objects in the system here. So our system consists of all three objects. Okay, so there's change in kinetic energy of all three objects. So what we want to do is we want to look at this, this work term. So the work, let me just get rid of this because we're going to need a little bit of room here. So the work done by all of the forces, there are a whole bunch of forces in this example. Okay, so not only are there forces of gravity, okay, acting on big M, acting through a displacement, so big mg acting through a displacement h, and little mg acting through a displacement h in the opposite direction. So there's work done, energy transfer by the gravitational forces, two of those work terms. There's also, in this system, you've got this rope is under tension T, which means that it is acting on big M. There's a force on big M that's upwards as M is displaced downwards. So that T is doing work. It's transferring energy. Okay, and this T, this tension T, is also being applied at this point, and so it's exerting a counterclockwise torque. Okay, so there's a torque being applied while the pulley is undergoing angular displacement, and so there's energy transfer associated with that as well. There's energy transfer here. There's energy transfer associated with similarly with the tension little t in the right-hand rope acting through a displacement here and acting through an angular displacement here. Okay, so there's lots of forces moving through linear displacements or torques moving through angular displacements. So there's lots of work terms. So there's the work done by the tension force T acting on M as it goes, big M, as it goes through its displacement. So there's a WT on M, plus there's a work of the tension force big T, which is applied to the wheel at that point. It's exerting a torque, and there's a torque acting through an angular displacement. So T on ICM plus, similarly, there's a work for little t on little m and little t on ICM. So work of the tension little t on little m plus work of the tension little t on ICM on the pulley. Okay, so we have 5 work terms there. Now, this is really interesting. So first of all, let's look at this term, the work done by the tension force T on big M. Okay, so this, because the force of gravity is constant, and the acceleration here we know is constant, we figured that out, this tension is also constant. Okay, so we have a constant force acting through some displacement, and so the work done is just the constant force vector, which is a vector of magnitude t pointing up, vector dot product with the displacement of a magnitude h downwards of m. Okay, and so this thing looks like we have a mass, big M, and there's a force of magnitude t in the upwards direction, and there's a displacement of magnitude h in the downwards direction. And so work for under a constant force is just force vector dot product with the displacement, and so that's vector t, vector dot product that, so it's going to be negative because they're in opposite directions, and its magnitude is the magnitude of the tension times the height. So this is negative capital T times h. Okay, now this one is a little bit more interesting. For this one, what we've got is this situation. We've got a wheel which is rotating, and we have a tension T applied at this point downwards. There's a moment arm distance r, so there's a torque, a counterclockwise torque, okay, acting on that wheel. And so, so let's see, we have the work done, so this WT on ICM, I'm going to run out of room here. That work is equal to, we know that the work done by a constant force acting through displacement is F delta x. A constant torque acting through an angular displacement delta theta is the torque, that constant torque, times the angular displacement delta theta. So now, as we just talked about over here, actually previously, we had when big M falls through a distance h, then the wheel rotates through an angular displacement such that h is the arc length that it rotates through. Okay, so on this picture over here, we have the wheel will rotate such that this point will move through an arc length h, and the radius of the wheel is r, and so there's a certain angular displacement delta theta. So it's the torque times the angular displacement delta theta. So we can work that out. So let's see, so what is the torque? Well, if we're looking at the torque that's produced by a tension force capital T, well, that's going to be a counterclockwise torque. Okay, it's a counterclockwise torque, and it's also a counterclockwise angular displacement. They're both counterclockwise, so they're both in the same direction, so the work will be positive. Okay, and so the magnitude of the torque is the moment arm r times the perpendicular force T, r cross F. Okay, so r times T, so it's a r times T, and then delta theta, we know that h is equal to r times delta theta, so delta theta is h divided by r. Okay, and so then the two r's cancel out, and we have positive capital T times h. So this work done by the left-hand rope under tension capital T acting and exerting a torque on the pulley is positive TH. And so you see that this work term and that work term exactly cancel each other out. Okay? And similarly, you can look at these two terms, the work done by little t on little m and by little t through a torque on the pulley. Okay, and so that turns out to be a positive TH, little th, and a negative little th. Okay, so the work done by little t on little m, well, the force is in that direction and the displacement is in that direction. So the vector dot product force dot displacement is positive, and it's of magnitude little t times the height h that it moves up through. That's positive little th. And you can see that the wheel is rotating this way, counterclockwise, but the torque that little t applies is clockwise. Okay, and so the torque and the angular displacement have opposite signs, and so you will get a negative t times h. And then these two terms separately cancel out, so that's 0 plus 0. And so all we're left with is the work done by the gravitational forces acting on big M and little m. As one of them goes down, work done by gravity is positive, and one of them goes up, work done by gravity is negative. And remember that the work done by the gravitational field, here's a system. The work done by the gravitational field is the energy transferred to that system. Okay, and so if that's positive, then energy has been removed from the gravitational field, and so the change in the gravitational field energy is negative. So the work done by gravity is just negative the change in the gravitational field energy. Okay, and so what we end up with is, you can just see, work total is change in kinetic, and so we have the work total, we just worked that out, is negative delta change in the gravitational field energy. Well, that's equal to delta kinetic. Okay, so the gravitational field energy went down, delta U gravity is negative, the negative of negative is positive, which is the positive change in the kinetic energy of all three of these objects in motion. Okay, and so you can see that this is exactly the same as conservation of total energy. Okay, so all I do is I just take the negative delta U gravity over to the right-hand side, and it says that delta kinetic plus delta U gravity is equal to 0. Well, that's just delta E total. Okay, so just a quick recap here. So what we've done is we have solved the famous Atwood machine problem, and we solved that problem 3 different ways. So we solved it using dynamics, and we solved it using conservation of energy in the form of the total energy in an isolated system can't change. And now we've just solved it in terms of energy transfer. Okay, so work is energy transfer. And we see that, work as energy transfer, it says the same thing as the total energy of an isolated system remains constant. Okay, so that's great. And it's super important that you know how to solve, problems like this using a variety of different approaches, dynamics and energy conservation approaches and so on. But what you really want to do in physics is not just learn how to, solve problems like this. What you want to do is you want to use those problems to extract a deeper understanding and a deeper intuition about how nature actually works. Okay, and this energy transfer, analyzing a problem in terms of energy transfer often reveals some really interesting aspects of the way nature gets stuff done. Okay, it's super cool. So let me show you what I mean in this example. Okay, so what we've basically got here is we've got this pulley, and we've got a mass big M attached to it, and that mass big M falls through some height h and lands on the ground. And then we had a mass little m, which started on the ground, and it rose up the same height h, like this. Okay, so we had this situation going on. So there's linear displacements h, and there's also some angular displacement delta theta that goes on with that wheel. Okay, so now during this process, like that, during that process, there has been a whole bunch of energy transfers happening. Okay, so the first energy transfer to think about is the energy transferred or the work done by gravity on big M. So when the force is constant, which it is the gravitational force, then the work done is just force dot finite displacement. So we have a force of magnitude mg down, vector dot product with a displacement of magnitude h down. And so the energy transferred to the system from the gravitational field is positive mgh. Okay, so that's the first thing to recognize. During this fall, there's an amount of energy, positive big M G H, transferred to that mass. Now, if we didn't have that mass attached to a rope that's under tension, exerting an upward force, if we just cut the rope, then that mass would free fall, and all of that gravitational field energy would be converted into kinetic energy, and big M would hit the ground moving fast. Okay? But because big M is connected to everything else here through this rope, and that rope is under tension, it is exerting an upward force, and it is preventing all of that gravitational field energy from being converted into kinetic energy. Only some of it gets converted into kinetic energy, and some of it has to go elsewhere. And so where it goes is up the rope into the pulley. Okay, so let's think about that a little bit. So when we're talking about big M, so for big M, we have gravitational field energy goes in. So there's a positive mgh flows in to big M. Okay. However, the work done by this tension, this upward tension force on big M, it's an upward force, it's a downward displacement. The work done by that tension force on M is negative. It's this thing. Work done by big T on big M is negative TH. So the action of that upward force acting through a downward displacement transfers negative energy to big M, which is the same as pulling positive energy out. So it pulls an amount of positive energy out, okay, so equal to capital TH. So it's positive mgh in, it's capital TH out, okay? And so the net transfer, let's indicate it this way. So, yeah, mgh in, but capital TH out. So then the net energy transferred to that mass, which goes into kinetic energy, because that's the only way that mass M can store energy. So that is then the change in the kinetic energy of big M. And that change in kinetic energy of big M is the energy in minus the energy out. So that's mgh minus th. The common factor is h. So that's mg minus t times h. So what's mg minus t? I don't know. So mg, that's the net downward force. Okay, so mg is the downward force of gravity. T is the upward force. The net downward force is mg minus t times the downward displacement of h is the work done by the net force. The net force is mg minus t, and that force acting over displacement h is the net work done. mg minus th is the net work done, which is the energy transferred to M, which is the change in the kinetic energy of M. So that's the net, or the total energy transferred to big M. So W total superscript M. Okay, so that, first of all, makes some kind of sense, hopefully. And then the idea is, well, great. So this energy TH, which is taken from big M, and prevents it from converting all of the gravitational field energy into kinetic energy. It hits the ground slower. Okay, that energy TH flows up the rope here, and it flows in to this wheel, to this pulley. Okay, so we have, let me see, so regarding the pulley, which will denote ICM, regarding the pulley, we have an energy TH flowing in. So TH flows in, okay? And then what flows out? Well, let's see. We have a tension T acting at this point, okay? And so that's exerting a clockwise torque, but the angular displacement is counterclockwise. And so the energy transfer is torque times angular displacement. Because they're in opposite directions, torque is this way, angular displacement is this way, it's negative. Okay, and so this is the work done by little t on ICM, and so that's negative. You can say, so the energy transferred to the pulley is negative little th. So the energy transferred out is positive little th. Okay, so what comes out is an amount of energy little th. So big th in, little th out. Okay, And so energy in minus energy out is the change in the energy of the system. Well, the system can only store energy in kinetic energy, in this case, kinetic energy associated with rotation. So the change in the kinetic energy of ICM, of the pulley, well, what's that going to be? It's the energy in minus energy out. So it's TH minus little th. So factoring out the h, that's big T minus little t times h. Okay? And now, you think about that for a second. Let's multiply the first term by big R and divide the second term by little r, so that doesn't change anything. So that's equal to big R times big T minus little t times h divided by big R. Okay? Now, each of these terms has clear meaning in terms of torque and angular displacement. Okay, so big R times T is the counterclockwise. So big R times T is the counterclockwise torque. Big R times little t is the clockwise torque, and the difference is the net counterclockwise torque. So big R times big T minus little t, that's the net torque acting on that, that wheel. And h divided by r, so remember that, this distance here is h. And so h divided by the radial, the radius of the wheel is delta theta. That's the angular displacement of that wheel. So this is net torque times angular displacement. Oh, energy transfer is torque times angular displacement. This is net torque times angular displacement is net work done. Okay, is net energy transferred. So this is the total work done by these twisting forces, by these torques, acting through an angular displacement delta theta. So that's the net work done on ICM. So that's right. Okay, and then finally, we look at little m here. So for little m, it's the same kind of an analysis. We say, okay, first of all, we have an energy, oh, my little microphone fell down here. Well, maybe it'll still be okay. Okay, so we have the mass little m, and then so we say how much energy flows into little m. Well, this TH flows down the rope, and we have a TH. How did I want to draw that? Yeah, a little TH, which flows into m. However, you'll notice that m is rising up. And so because it rises up, there's energy transferred into the gravitational field. The work done by the gravitational field is the gravitational force, little mg down, vector dot product with the finite displacement, positive h up. Okay, and so that's negative little mgh. So that energy, the gravitational field added negative mgh energy to it. So the gravitational field itself increased by an amount, positive mgh. So there was an amount of energy mgh which flowed out. Positive little mgh flows out back into the gravitational field. Okay, so when we're talking about little m here, we have how much energy flowed in during this process. Well, an amount of energy little th flowed in. How much energy flowed out? Well, positive mgh, little mgh flowed out. Okay, that was the energy that went back into the gravitational field. Some came from the gravitational field, and then some goes back out, because this guy went down, so it took energy out of the gravitational field. Little m went up, so it put energy back into the gravitational field. Okay, and so the total amount of energy that goes into little m is the th that flows along that rope minus little mgh. Okay, so that tells you that the change in the kinetic energy of little m must equal energy in, th, minus energy out, little mgh. What's common is the factor h, and so this is t minus mg times h. Okay, we look, well, what is that? I don't know, what's t minus mg? Well, t minus mg is the net upward force that's acting on little m over a displacement of h upwards is the net work done by all of the forces on m. It's the net energy transferred. It's the work done. It's the net work done by all of the forces acting on little m. So this is the total work done by all of the forces on little m. Okay, and it all works out. Gravitational energy flows in. Okay, not all of it is converted to kinetic energy of big M. Okay, because you have this rope is under tension. It's holding it back. It doesn't allow it just to free fall. And so then it sucks out of it an amount of energy, big TH, okay, which goes into the pulley. Okay, but oh, wait a minute. We have a rope acting in this direction. It's a clockwise torque, counterclockwise displacement. The energy flowing in is negative, which means positive energy flowing out. So little th flows out. Big TH flows in, little th flows out. And the difference is precisely the change in the kinetic energy of that rotating pulley. Okay, so then we have this energy TH flowing down that rope. Well, where's it going to go? Well, it's going to go into little m. Oh, but wait, not all of it will go into little m because some of it gets because little m is rising up. So the energy, some of the energy has to flow back into the gravitational field. So the amount of energy that actually flows into little m is little th minus little mgh. And that, of course, is the net force times the displacement of big M. It's the change in the kinetic energy of little m. So it's really, really beautiful. So I hope that you can, solve this problem, properly using dynamics and using conservation of energy in terms of delta E total equals 0 or the work kinetic energy theorem. But then also stuff like this. This is the stuff that's really interesting to understand. Okay. So the final way that we're going to look at this is we're going to look at this Atwood machine in the context of power, rate of energy flow. All right? So I'll just erase the board and be right back. Okay, so finally we're going to look at this Atwood machine from the point of view of power, rates of energy transfer. And this is really interesting as well. Okay, so that's I guess part D here. We're going to look at it from the point of view of power, or rates of energy transfer. So the first thing to note, well actually let me draw this diagram first so we know how much room we need. So we've got, let's put it sort of right in the middle here. So we've got this pulley and we've got it attached to these masses. Okay, so there's a mass big M, and there's a mass little m. And what else? So big M is accelerating downwards with acceleration little a, and little m is accelerating upward with the same acceleration. And just before, well actually we're going to take v here to be the velocity at any instant of time. V starts at 0 and it ends up with this final velocity v that we calculated. So when I write v here, I really mean a velocity which is a function of time. So it'll start at 0 and it'll increase until it reaches that final value. Okay, and little m is moving upwards with an instantaneous speed v. Now that's important because power is force dot velocity, so we need velocities in here. Okay. So we've got that, and what else? We know that the rope on the left-hand side is under tension big T, the rope on the right-hand side is under tension little t, and we are going to consider as our system, we're going to consider just this. Okay, so the gravitational field will be outside of the system. Okay, so the system just consists of the masses little m, big M, and this pulley with moment of inertia ICM. Okay, so this is our system. And what else? And this this pulley is, there's a constant linear acceleration of these masses, big M down and little m up. There's at the same time a constant angular acceleration alpha of this pulley in the counterclockwise direction. And at any instant of time, we're going to denote its angular velocity, radians per second, as omega. Omega starts at 0 and then ends at the final value that we calculated before. Okay, so we have that. And I guess we're ready to begin. So I just want to sort of point out that omega and v are increasing, are constantly increasing. They start at 0 and then they increase as time goes on, which means that the kinetic energy stored in m and the kinetic energy stored in little m and the kinetic energy stored in the pulley KICM, those are also increasing. Okay, and so the kinetic energy of all three of these objects is increasing, and the rate at which they're increasing is going to be the net power that's being supplied to those objects. So there's power flowing into each of these things. So there's power. And we're going to be looking at the rate at which these kinetic energies are increasing. Okay? So let's start with this statement here. That remember that power is force dot velocity. Okay? So we're going to draw an arrow, a big wide arrow here. Okay, and this arrow represents energy flowing in. From where? From the gravitational field. So the gravitational field is on this side, and the three masses are on this side. And there's gravitational energy, some gravitational energy flowing in to big M, and a lesser amount of gravitational energy flowing out. So there's a net net flow of gravitational energy, or decrease in gravitational energy here, and that corresponds to an increase in kinetic energy on the other side, inside this system, okay? So there's a big fat, think of these as pipes. I'm going to show you a bunch of little pipes, and think of them as water flowing in the pipes, okay? So the first thing is the power into the system, and this is gravitational power. So power is the rate at which energy is flowing. It's the rate of change of the energy. Rate of energy transfer, and that power is the force dot the velocity. So we think about the gravitational force. The gravitational force on big M is a force of magnitude mg down, vector dot product with the velocity, which is also down. So it's positive, so this is equal to positive mgv. Okay, so when the velocity is 0, the system starts out at rest and you let go. When that velocity is 0, the power, the rate at which gravitational energy is flowing in and being converted into other forms of energy, namely kinetic, is 0. Okay, but then as big M and little m increase their speeds, and big M increases its speed, then the power, the rate at which energy is being transferred from the gravitational field into this system increases. Okay, so this is the real thing driving the system, is that gravitational energy flowing in at a rate that's proportional to the velocity. It increases as as the speed of m increases. So this is power is joules per second. It's number of joules per second that's flowing into the system from the gravitational field that's outside. Okay, so then we need to ask the question, well, great, we've got this joules per second energy coming in. Okay, what is the rate at which big M is absorbing that energy? Okay, well, let's work that out. So M, so I don't have a lot of room here. So M absorbs energy at a certain rate. So absorbs energy at a certain rate, and that rate is the time rate of change of its kinetic energy. The kinetic energy of a mass m moving with speed v is 1/2 big M v squared. Okay, so what is the time rate of change of that? Well, m is constant, so the time derivative of v squared is 2v times the time derivative of v is the acceleration. So we get mass times acceleration times velocity. This is what this thing is. So it's the mass of this block times the downwards acceleration of that block times the downwards velocity of that block at any instant time. M and A are constant, but V is increasing linearly with time. Okay, so, but what is mass times acceleration of big M? Well, it's the net force acting on big M. Okay, so it's equal to the net force acting on big M. And that's times the velocity. So it's force times the velocity. I can just get rid of this m, actually. Let's just leave it like that. It's just the net force acting on big M times the velocity. The net force is downwards. The gravitational force is stronger downwards than the tension force up. There's a net acceleration downwards. Net force is down. The velocity is down. This is F dot V. This is power. So this is the rate at which energy is flowing into M, which is changing its kinetic energy. Okay, so the net force, and that net force is mg down minus t up times the velocity. Okay, so we have that. So so what that means is that the power flowing into this system, into M, from the gravitational field is big M GV. That's coming in. However, the amount of energy that M is absorbing is only mgv minus TV. So it's not absorbing the full mgv. Okay, there's a minus TV that is not absorbing. And so that minus TV goes up the rope, is transferred up the rope. So the amount of power, the rate at which energy is being transferred, the amount of power that goes into big M, okay, is this thing, mg minus TV. mg minus t times v. That's the net rate of change, net power flowing into M, the net rate of change of the kinetic energy of M. So this amount is sort of bled off. We have a big pipe of energy, of power coming in here, mgv. This little amount is bled off, mg minus t times v. So mgv minus mg minus tv is positive tv. So what's left over is positive tv. And that flows up along this along this rope under tension T. So that flows up like this. So this amount that's left over inside here is TV. That's the rate of energy flow, the number of joules per second flowing along that rope into the rest of the system. Okay? Okay, great. So then the next thing to say is if we look at ICM, so by that I mean the pulley. So let's look at that pulley. And let's ask exactly the same question. So this pulley is absorbing energy at a certain rate. And the rate at which it's absorbing energy is, the rate of change. The only way that the pulley can store energy is in its energy of motion, is in its kinetic energy. So the rate at which it's absorbing energy is the rate of change of its kinetic energy. The kinetic energy of an object in rotation is 1/2 its moment of inertia about whatever axis it's spinning, in this case center of mass, times omega squared. Okay, great. So then you do the same thing. You say, well, the time derivative, this is constant, that's constant. The time derivative of omega squared is twice omega times the time derivative of omega. That's twice omega times alpha, the angular acceleration. So the twice cancels at half, and what we end up with is ICM, the moment of inertia, times the angular acceleration alpha times the angular velocity omega. Exactly the same as this. Instead of linear mass or inertia times linear acceleration times linear velocity, it's angular inertia or moment of inertia times angular acceleration times angular velocity. Same thing. Okay. All of these angular sort of analysis of angular motion is exactly analogous to translational motion. Okay, so ICM times alpha, what's that? Like mass times acceleration is force, net force. And so ICM times alpha is net torque. Okay, so what we have is the net torque. It's the net torque acting on that pulley. There's a counterclockwise torque because of the tension big T in the left rope. There's a clockwise torque because of the tension little t in the right rope. The net torque is a counterclockwise torque because big T is bigger than little t. Okay, so that's the net torque times omega. Okay, and so that net torque, so what is that net torque? Well, that net torque is the radius here is r. We have a force T down at that point and a lever arm r. Or a moment arm. So R times T is a counterclockwise torque. So it's R times T is the counterclockwise torque. And then we subtract the clockwise torque, which is R times little t. So it's that's the net torque times omega. And that thing is the same thing as, remember, R times omega. Omega is in radians per second. And R times omega is the tangential velocity of points of any point on the rim of the wheel. And it also matches the linear velocity of big M and little m, which is what we called v. So this is the same thing as big T minus little t times the velocity v. Okay, so that's good. So this is the rate at which ICM is absorbing energy in the form of kinetic energy. So what that means is this pipe of power which is coming in, some of it gets bled off into the wheel, into the pulley. And the amount that's bled off into the wheel is big T minus little t times v. So that's a big T minus little t times V is the amount of power, the rate at which energy is entering, the net energy is entering that wheel. That pulley, it's the rate of change of the kinetic energy of that pulley. Great. And so what we have is this pipe has a power of TV, a big power of TV. Some of it is bled off, big T minus little t times V. And so the difference is little t times V. So that little t times V is left over. And so it sort of schematically, still power flow within the system. But where does it go? Well, now it's going to flow down down the rope on the right-hand side. So this is a power conduit with an intensity little t times V. So after you've bled off big TV, you've bled off that little bit, and you're left with little TV, is the power coming down, being transferred down that rope. And that little TV, instead of all of that little TV going into little m, what happens is, because little m is rising up, it means that there's energy being transferred into the gravitational field. So out of our big M, little m ICM system. Remember, gravity is outside here. Okay, and so it's going to go outside the system. Okay, so let's then look at this. Let's look at mass little m. So mass little m, what is the rate at which mass little m is absorbing energy? In this case, in the form of kinetic energy. So it is absorbing, little m is absorbing energy at the following rate. Well, the time derivative of its kinetic energy. So with the kinetic energy of little m is 1/2 m little v squared. Okay, so the 1/2 and the m are constant. The time derivative of v squared is 2v times the time derivative of v. That's 2v times the acceleration of little m. Okay, times the half there. What you get is a little m times the upwards acceleration of little m times the upwards velocity of little m. Just like this, big M AV, it's little m AV. Okay, and so, well, little m, mass times acceleration is net force. Okay, and so that's the net force, the net upward force in this case, because the acceleration is upward. It's the net upward force acting on little m. And so what's that? So let me just write it this way. So it's the net force acting on little m times the velocity of little m, because that net force is upwards and that velocity is upwards. So force dot velocity's power is positive there. Okay, so so what? So what's F net? Well, the net force, the net upward force is T minus little mg. So it's little t minus little mg, and that gets multiplied by the velocity v. Okay, so this is really nice. So what we have is there's a power conduit coming down with an intensity of little TV. Not all of that little TV power goes into M. The amount of power that goes into M is smaller. Okay, and the amount that goes into M is little t minus mg times v. Okay, so we started with a power conduit of intensity little tv. Some of it was bled off and goes into changing the kinetic energy of little m. And so this minus this is the amount that can't be absorbed, which is dumped back out into the gravitational field. So little tv minus this expression is positive little mg. So this is positive little positive little mg times v. Okay? And so, but that's exactly the power flowing back into the gravitational field, because remember, the gravitational field is exerting a force of magnitude little mg down. The displacement is of magnitude h up. And so, the velocity is up. So the power is force dot velocity. So the force is little mg down, the velocity is little v up, so the dot product is negative. So the power flowing into the system, the gravitational power flowing into the system is mg, the gravitational force, vector dot product with the velocity. But mg and the velocity are in opposite directions, so this is negative mgv. So the gravitational power flowing in is negative mg, so the gravitational power flowing out of the system is positive mg. So this is power out gravity. Isn't that cool? Okay, so at the end of the day, and it's flowing out, of course, because M is rising up. And so there's energy being transferred into the gravitational field. And there it is. So this is awesome. I mean, to think about systems like this in terms of energy flow, and in this case, power flow, rates of flow of energy. We have this conduit of power. The main thing powering this Atwood machine is gravitational energy flowing in. Okay, energy flowing in from the gravitational field and being converted into various forms of energy, kinetic energy here, and then whatever's left over gets dumped back out into the gravitational field. So there's more power flowing in from the gravitational field than out. So there is a net power flowing in from the gravitational field. So where's that power going? Well, it's powering little m and big M picking up speed, gaining kinetic energy, and the pulley picking up angular velocity, also picking up kinetic energy. So that power, the rate of energy flow, is is determined by this. It's just super cool. When you think about how energy flows around, it's a really beautiful thing. So yeah, it's great to understand all of this stuff and be able to solve these problems, but it's also really nice to be able to look in a little bit more depth. So that's what we're trying to do in 121, is make sure that you guys understand the beauty of how nature gets things done, and understand the idea of energy conservation in a little bit more depth. This is a great example. I love this example.